Hey, so we'll begin going through the second lecture in the series, which is neural networks for mathematicians, and we'll be stepping through the neural network architecture. But before we begin, the first thing we'll do is actually step through a simpler example of solving a linear transformation using PCA. So we'll walk through the steps of solving principal component analysis, and then we'll move on to looking at the same data set, however solving for a lower dimensionality space using an autoencoder. So the reason why we do a linear transformation first is because it's really important to understand the steps of matrix decomposition before moving on to something more complicated, such as learning via neural networks. So just a reminder of the data set that we're using. So we've only got 3 features, which is our BMI, the years smoked, and the age of the patient. And we're trying to transform these down to just 2 dimensions. So it's a pretty simple example. And we went through this in quite some detail in the previous lecture, but the question comes, how did we actually compute these? So this is the overview of the steps to PCA, however we'll be walking through each of these in detail. So the first thing is centering the data, then we'll compute the covariance on the centered data, then we'll compute the eigenvectors of the covariance matrix, we'll sort these by their largest eigenvalue, and finally we'll transform our center data using the top n eigenvectors. So the first bit, center the data, all that means is we take the mean of our data, so the mean of each row, and then we subtract that from our data. So that means our data becomes centered around 0. This is one of the steps in standardizing our data, so if you've already standardized your data, you don't need to perform this step as well. So to give you an idea of how your covariance matrix, which is the next step in PCA, corresponds to something people are probably more familiar with, which is your correlation matrix. It's just your correlation matrix is your covariance standardized. So it's your mean on your number of variables essentially, and if you're taking the correlation of that, you divide that by your standard deviation. So we can see the correlation matrix here for our 3 features. If we compute our covariance on the unstandardized data, we note that it's quite different. However, if we compute it on the standardized data, so we've already actually performed this division by standard deviation and we've transformed our data to have a standard deviation of 1, then our covariance matrix is actually just our correlation matrix. The next step is computing the eigenvalues and the eigenvectors of the covariance matrix. So you'll notice the familiar process of computing your eigenvalues and eigenvectors by hand, but fortunately we don't need to do that. We can just use a library such as NumPy, which has eigenvalue decomposition solvers already. But what's more important than understanding how to solve this by hand is understanding what your eigenvalues and eigenvectors are. So your eigenvectors are essentially the only vectors in the space. So if you consider A to be a matrix that forms a linear transformation on your data, which is all that a matrix is doing, your vectors are the ones that aren't changed in terms of direction. So they aren't rotated or anything like that. They're just lengthened. So basically all they are is transformed by a scalar multiple, which is your eigenvalues. And so how long or short they get contracted, that's your lambda. So what we're looking for in PCA is actually the eigenvectors that correspond to our largest eigenvalues. So the ones that, rather than getting rotated, those vectors that just get stretched the most, which is our components of most variation, because we're performing this on the covariance matrix. So what you can do is you can get your tops PCs by sorting your eigenvalues to get the biggest one, which corresponds to your top principal component, which, as I said, corresponds to that direction of variance, the one that gets stretched the most. So you can perform this in NumPy just using the sorting function to get the indices, and then you sort your eigenvectors by those eigenvalues. And what we can see is why our largest eigenvalue is 1.17, etc. So the next way that we actually get our principal components is we perform matrix multiplication by our eigenvectors and our centered data. So our just data matrix that was centered on 0, or our standardized one if we use that as our input, because we were trying to normalize our data in that way. And what we get is actually the same principal components that we got by using the input, the classic function in SciPy or scikit-learn, I can't remember which one, which is just the PCA. So you can either compute the steps manually, which I would recommend doing just to try it out, because it's always good to, confirm your understanding, Or alternatively, you could just use your libraries and do it in 2 lines. So whatever works best for you. So as you notice, usually PCA is used to reduce the dimensionality of your dataset. And whenever you reduce the dimensionality, normally there's a trade-off, as in you lose some sort of information. So you can never reconstruct your input space completely. So the question becomes, if we're reducing our dimensions from 3 to 1, how much information do we lose? And when we try to reconstruct our original space, our original 3D space from just one principal component, it looks like we've lost a fair bit of information. Surprisingly, from 2 principal components, we can reconstruct quite a bit of the variation within our dataset, and we notice that when we use 3 principal components, which is the entire feature space of our dataset, we can reconstruct it perfectly. So that's something to keep in mind. No information is lost in PCA by the process of performing the decomposition. It's only lost when you reduce the number of principal components to be less than your original input space feature set. And so there's lots of different ways that you can choose the number of principal components that are optimal for what you're looking into, like a scree plot, but we're not really going to dive into that too much. So now that you understand the simple principles in eigenvalue decomposition and what, matrix multiplication essentially is doing, we're going to go through this example again, but this time we're going to use a neural network to solve our system. So we have the same example from the previous video. So again, we've got our 3 featured data set, and this is an example of what the output of the autoencoder function was for one of our examples. And again, what we're going to do is we're going to use a very simple architecture because it's easier to walk through and hopefully easier for people to understand, where we just have our 3 input features connected to with a fully connected layer, which means that we've got weights going to each of our encoding variables, and then a fully connected output layer again to our 3 outputs, which are approximations of our input with some sort of reconstruction error. So this is just my summary of the steps to learning using an autoencoder, which is a neural network for reconstructing itself. So the first step is to separate data into a training and test set. I know that this has already been covered previously, but essentially you'll want to make sure that you capture enough variation in your training set, but you don't want to overfit. So you want to have some held out data so you can validate that your network hasn't just learned to recreate data that it's already seen. So 75 to 80% is usually all right split, depending on how big your data is. Next, what you do is you encode some of that data using weights and biases, which becomes your encoding function. Then you decode that encoded data using, again, some weights and biases, which is your decoding function. And then you compute the loss for that iteration. So that may be a single data point or a batch, depending on how you define things and choose to do it. And basically now you want to propagate that loss through the system. So you do that by computing the gradient and solving for each parameter, and propagating that through from the output all the way through to the input. And then you repeat that for a certain number of epochs until your loss has stabilized. And then finally you test your trained model on the test set, so that held out data. So this is pretty abstract, but I'll be going through each of these steps over the next number of slides, so please stay with me. So again, this 3-dimensional data set that we're trying to encode down to 2 features. So I'm just showing you what an input is. So an input is just a vector, which is 3 features for a single patient. So keep in mind that these are the standardized features, so they'll be centered around 0 and have a standard deviation of 1 approximately. So just to reiterate what I said on the first slide, the learnt value, so the parts of the network that are the parameters of functions that we're aiming to optimize, are the weights and the biases. So you can think of the values that are unique to each data point being your input, so this is depending on a particular patient. Your encoding will be dependent on that patient and biased by, well, multiplied or parameterized by the features that we've learned, so those weights and biases, but that should be unique, relatively unique at least to a patient or a data point. And finally, the output again is dependent on your input, so relatively unique, it's not a learnt feature. And then the nonlinearities are these activation functions that occur before each of our layers in the network and also our output. So the first thing that we need to note is after we've got our input variables, we have a series of weights for this encoding function. So those weights were previously described by these arrows essentially pointing to the encoding data. But all this one is a 3x2 matrix that you multiply your input data point by. And so I just wanted to show this because when I first learned about neural networks, it seemed like a really scary or obscure black box, which, you didn't really look into. You couldn't understand what was going on. It was pretty, obscure. But all it is, when I actually started looking into it, is just a matrix that you can multiply data by, which is kind of cool. It's very easy. It's understandable. It's exactly what we did in PCA. And I hope you all bared with me and understood PCA. So if you can understand PCA, you understand the fundamentals of a neural network. So you've got your 1x2 encoding, and to get that, you've got your 1x3 input vector multiplied. So it's one row of 3 features multiplied by 3 rows of 2 features, which is your weight matrix. So it's important to keep in mind how matrices are able to be multiplied together, because that is an error that does encounter quite often. So we'll go through that in a little bit more detail in the next slide. So just in case any of you haven't seen matrix multiplication before, it's less complicated than it looks. Essentially, you take each row and you multiply it by each column in the second data set. And that's why the internal numbers need to match. So a 1x3 needs to be then by a 3 by some other number. So the internal numbers must match. So again, it's just the sum of each of those values multiplied by each other. You also don't need to do this by hand. Again, we use code to solve almost everything nowadays. At least I do, because I'm a programmer, not a mathematician. Sorry, mathematicians. So you can just use NumPy to do a matrix multiplication of your input matrix multiplied by your encoding weights. And as you can see, we said before, it will give you a 1x2 array, and that's exactly what we get out. The next bit of the walking through the network is the biases. So the biases are a scalar multiplier, and that just means it's a scaling number. So it's a number that makes it bigger or smaller. And the bias is used to scale the effect of the node, not manually, but basically by the network. The next step is the activation function, and that squashes your values or projects your values to a certain range. So it's typically termed the nonlinearities of the system, and a classic example is the sigmoid function. So if you consider your x values as the inputs, so our input data multiplied by our bias and our weights, and then we project it through here, and it gets scaled to our y values, which is between 0 and 1. And that basically, we can use sigmoid. There are lots of other ones, and we discussed that in the previous lecture, and we showed how they, transform your data to certain ranges and why that might be useful. So the next thing, so we've got our encoding function. How easy was that, right? All you did was take an input variable, multiply by some weights, some biases, and then put it through a squashing function, essentially. So not too hard. The next bit is decoding, which is essentially the exact same thing, but transforming it back to our original input space. So we want to get a 1x3 matrix, and we've got a 1x2. That means the weights, by necessity, must be a 2x3 shape. Of course, you can have multiple layers of these, but I'm just showing one layer to make it easy and a short-ish video. So again, we do the same code. It's just our vector of our encoding space multiplied by our weights of our decoding, and that gives us our 1x3 that we need for our output. Again, this gets multiplied by a bias vector, which is again just a scalar multiplier, so just a number for each output essentially. And then we put this again through another activation function. So this may be the sigmoid. If you're doing a binary classification, it might be a 1 or a softmax function. It really depends on what you're trying to solve in your system and what you expect the outputs to be. So that was super easy, right? So we've done a full step through of the neural network. And then the question comes, okay, how does it actually learn? Now we can, walk through it. How does it know, and how does it learn the optimal weights, because essentially that's what we're doing. We're trying to learn those parameters, which are our weights and our biases. So originally, when you start off, your weights are just usually assigned a random number between 0 and some small number, and then we want to learn what the weights are optimal for the system. So in order to do that, we need to compute a loss that's meaningful. So we need to be able to tell the network, this is not close to what your input was, or yeah, nice, you're killing it, this was really close to your input. So this again depends on what you're trying to learn. So if you're learning something which the distance is in Euclidean space, so you basically want to compare things together. So for example, if you've got gene expression data, you'd want to use mean squared error. So that's basically just taking in the relative difference between things. If you had binary data, you'd want to look at something different. So you'd want to use something like cross entropy, which takes into account distances for binarized data. For example, this would be important for something like transcription factor binding sites, because that's either it's binding or it's not binding. It's not a relative level like expression. So the question really is, what is the loss that makes sense in identifying whether two data points are similar or far away from each other? So for this example, I decided that a good loss would be mean squared error, and so all I do to compute that is I compute the squared difference between my output, which is my reconstructed input, and my input. So for each one of these, I compute the difference. Now that we essentially have our function that we want to minimize, we've got our parameters. What we want to do is we want to tweak these parameters each time that we see data, and we want to tweak them in the direction that we're minimizing this loss. So we essentially have an optimization function where we want to pass our information from here, where we essentially find out what the error is, back through the network. So that's called our back propagation. And each of these steps, basically, we take the gradient of steepest descent. So what do I mean by gradient? If you remember from class, or think of it as Waddington's landscape, you want to move down that hill, and we can compute that by deriving it essentially. So we take it with respect to each of the parameters. You can go into more detail with this, and I do link some good notes at the end of this, but I won't dive into this now because this probably alone would take an hour or two to explain, because it involves a little bit of math. But you can also plot your error and just think of it as moving down the hill. The problem is, if you're moving downhill, you might get to a point where you think that you've stopped, and that might be a local minima. So the thing to keep in mind is that even if your loss has, stabilized, you might not be at the optimal solution, and that's one of the limitations of a neural network or any sort of machine learning algorithm. So it's not deterministic. We're not always going to end up in the same valley like we would with PCA, where it's a deterministic function and we always get the same solution. Something else to keep in mind is how far we're jumping down this hill. So if you see here, although this is a pretty smooth landscape, you might accidentally jump and then oscillate between points, and then you'll never reach a stable solution. So you want to make sure your steps are small enough that you can learn and tweak at each point. So the final bit comes to evaluating whether our neural network and our autoencoder has learned a good solution or a good dimensionality reduction. And the nice thing is we can actually, check out the output and our reconstruction at each point. So just like we reconstructed our principal component space using only one PC, and then we saw that it wasn't great, and then we did 2 PCs and we're like, cool, that's a bit better. And then 3 PCs, we're like, wait, it's contained everything. What we can do is we can plot our reconstruction in 3D space and see how well it matches to our original data set. Naturally, you won't be able to do this in most situations because most of the time you'll have a data set with way more than 3 dimensions, but for this contrived example, we can do it to understand what our system is doing. Lucky last, and I won't go into detail into classification, but I'm just going to say that it's essentially, if you're thinking of a fully connected dense network, it's almost the same architecture, and you'll notice this if you go into the notebook that I've provided along with these slides, that the classification uses the same architecture as our autoencoder. The only thing that's different is rather than trying to optimize our reconstruction loss, so we're trying to recreate the best version of ourselves, What we're doing is we're just actually trying to classify our data, so we're trying to get the labels correct. So that means we have a different loss function, so we use binary cross entropy, and rather than our input being our output is now a series of labels that we've assigned to our data using a one-hot encoding, which means we basically set it to 1 or it's zeros. So as you can see, this one's a kidney, and then the other ones go to lung. And it just so happens that we have 3 labels as well as 3 inputs. There's no rule for that at all. Lastly, I want you guys to think about, and I think it's really important to think about as a bioinformatician, is what's the best metric for determining whether our thing is good? So is accuracy the best way? So sometimes in biological data we could have a really imbalanced data set, or it could be really important that we, get one class correct. For example, if we get it wrong, it could lead to a patient's death, but a false positive could just lead to another test. So these are things to consider that you might not need to look into if you're doing, if you're working in another field. But for our field, these things are really important. So it's always important to think about this before you dive into just building a model and being like, cool, it gets 99% accuracy. So I hope that's given you a bit of a brief overview that neural nets are no longer like super scary. They're just, stepping through essentially a series of transformations, and that you understand a little bit with how they learn. So please check out these resources, and we'll be going through more material in class. So thanks for sticking with me. Cheers, guys.